I will try to go easy on you. So I will talk about one way to get digital signatures, and that is by starting from an identification scheme which you build using MPC in the hat. And let's jump right into it. I think mathematically this will be relatively easy to follow. So in general, post-quantum signatures is actually quite interesting because there are reasons why you might assume that signatures should be easier than CAMs. Signatures live from a complexity theoretic perspective in a world that's called mini-crypt, while CAMs live in cryptomania, which is containing mini-crypt, so you need something more complex than what you need for signatures. But actually, it turns out that building signatures in general is a bit more tricky for whatever reason. There are two main approaches. The first one is hash and sign, and I think Chris mentioned this a bit in his talk. So the idea is that you hash your message, and then, for example, I can use a trapdoor one-word permutation to invert on there, and that gives me the signature. This is what we do with RSA. In the case of lattices, we have the same thing. So Falcon is using this. There you actually use something called a pre-image sample of a trapdoor function. So it gets a bit more complicated, but the idea is the same. I have a function that I can invert on the hash function image, and this pre-image that I get from this trapdoor something function actually becomes my signature. Right? And then we have hash-based signatures, which also first hash the message, but then do something different, and I will talk about this tomorrow. The other approach, which is also widely used already today, is what ECDSA does, what Schnorr signatures do, and that's called Fiat-Shamir signatures. So you start with an identification scheme. Chris also briefly mentioned this, like you have an interactive protocol, then you make this non-interactive using something called the Fiat-Shamir transform, and that gives you a signature scheme. This is also what the lithium does. So I guess most people here have followed the NIST competition if they are here. So the lithium is one of the selected signature schemes. And that essentially tried to build Schnorr with lattices. And then you see that this does not entirely work. You have to do a little bit of playing around, and you have to reject some signatures because they might leak information that you don't want. But in the end, you can still follow the same principle. And then the last approach, which was kind of pioneered by Picnic in the first NIST competition, and now in the second one we have something like 8 schemes that all follow this approach, is this MPC in the hat approach. And this is what I will talk about today. Before I explain you how this works, why is this whole thing interesting? One example is the syndrome decoding in the hat signature scheme from, I will not pronounce these French names because I will just butcher them. But so this appeared at Crypto 22, and it is a code-based signature scheme which uses this MPC in the hat approach. And this actually beats all previous code-based signatures in terms of performance, if you look at overall performance. There are in some dimensions schemes which might be a little bit better, but if you look at the overall thing, nothing comes really close. And another really nice thing is, and Alex will explain a bit more about this in his talk, I think, this actually uses an unstructured version of the syndrome decoding problem. Like, you're not using syndrome decoding for some specific code or so, you're really doing this for a random code. And that makes it actually harder to break. And you can do the same thing for different problems. So we have the same thing for the MQ problem, where people build MPC in the hat signatures from MQ. But I actually worked a bit in this scheme, so I will use this scheme as a running example throughout the talk. So how does this whole thing work? On a very high level, the concept is as follows. I start with some one-way function, and in theory, I can actually take any one-way function for this. Then I turn this into an MPC computation by building a circuit which evaluates this one-way function on the input if it's given the secret sharing of this input. And I will explain what this means in a second. Then you have a multi-party computation where every party gets one share of the secret and they together evaluate the secret in some cryptographically secure way, whatever this means. Then there's a way, and this is what's called the MPC in the head paradigm, that you can turn such an MPC computation into an identification scheme. So you get an interactive protocol where the prover can prove that they know a secret corresponding to a public value, and this will be, the secret will be our X value, and the public value will be the evaluation of the function on input X, the one-way function. And it will do this in zero knowledge as long as the verifier behaves honestly. So from that we learn that actually you cannot learn anything about the secret when participating in this protocol as a verifier. And then we apply this Vier-Shamir paradigm to obtain a signature from this identification scheme. And depending on the time, I guess this last step I will more sketch than get into, but we will see. So let's start with the beginning. The one-way function and how to do this as an MPC computation. So as I said, as one-way function you can do almost anything. We've seen LowMC was a function specifically designed for the use in MPC computation, and it was used by Picnic. AIM is another function specifically designed for this use case, and it's used in AIMer. There was a version that kind of tried to do Picnic with AES called Feast. Then SD in the head actually does some one-way function which is polynomial arithmetic and evaluation. We will see what the one-way function actually is later. And then, for example, you've got Biscuit, which does, or MQ on my mind, which takes an MQ equation system of a certain form and evaluates that. The important thing is multiplicative depth should not be too much because you're actually paying quite hard for this. So every consecutive multiplication gate that you have will actually cost you a lot in terms of size and speed. And this is why you have these dedicated ciphers, LowMC and AIM. The problem is, I think LowMC is now at version 3 because this was actually broken several times, and AIM is also already at version 2, and this is much newer. So there's this tendency that people make it too easy when they are designing these low-depth ciphers. And so this is a bit risky. If you look at the other schemes, you can actually use these unstructured problems if you want. You can also use structured problems, which also people do, and they also tend to make mistakes in this. So Biscuit has a not too pleasant history right now. I'm not into this too much, but on the NIST mailing list there's currently a debate if it's broken or not. So I don't understand that one, but this is also about using too much structure. Okay, and then we start from this one-way function and we somehow turn this into a multi-party computation, which means we built an MPC protocol which allows n different parties, which I will call P1 to Pn, with inputs x1 to xn, to jointly evaluate some function such that all the parties in the end actually learn the outcome, but they don't learn anything beyond that. So obviously, if the function is sum and the outcome is 10, I know that the other inputs together would mine sum up to 10. So this information I cannot hide, right? But I shouldn't learn anything which I cannot derive from my own input and result. So as an example, if you consider, for example, negotiation between a buyer and a seller, and what they can do is they can compute if they agree on a given price X. So you just have to compute the logical end of a Boolean, which is, yeah, I'm willing to buy at this price and I'm willing to sell at this price, respectively. And you can do this in a way that actually, if they don't agree, the other party will not, so if you don't agree, you do not learn the other party's decision. If both parties agree, or if you agreed and the other did not, then you will actually learn the other party's decision. But as long as you say no, you will not learn anything about the other party, and this prevents, for example, pushing up or down, depending on which side you are, the price negotiations. The generic example that people use in school is stating, like, you can lift this to any kind of use case, but there you can maybe see where this gets interesting. And so there are protocols for this. In general, for many applications, we actually need somewhat simple ones, but we need some additional properties. So first we need perfect correctness. So we want that if all parties behave honestly, then the result should be correct. We want that even under corruption this thing is secure, so we want it to be n-1 private. So this means that if all parties collude against the last remaining one, they can actually still not learn the input of this last party, besides anything you can derive from the output of the computation again. And in our case, we're interested in protocols where the communication is broadcasted. So you don't have secret channels between the different parties, but just everyone puts their messages on a message board and everyone can see this, whatever communication medium you would use. In our case, this is anyway just written on a tape or written as part of a signature, so we don't care what you would use there. Any questions about this so far? Okay. A core ingredient that we will use is an additive secret sharing scheme, and this is as simple as it gets. You can think about this as a multiple times one-time pad. So you split a value x into the sum of random shares. There are different ways to do this. For example, you can pick n random shares and then you compute the delta of the sum of these with this remaining one, and you keep the delta in the mind, or you add it to the first entry, and then you have a random secret sharing of x. And this is a case where if you get all but one shares, then the final value is still information theoretically hidden, because this is actually a one-time pad, right? So there's nothing you can do to actually learn this value. And you can actually do a lot of operations with this. So when I'm writing this x in brackets, this means this is a value that's secret shared between n parties. And so, for example, I can add two shared values. And I do this by simply the parties locally adding their shares. Right? So if n parties have a share of x and a share of y, respectively, then they locally all just add their two shares. And if I'm recombining the resulting sharing, then I get the sum of all these local sums of x and y. And I mean, I can just compute this. This gives me the sum of the x plus the sum of y, which is the sharing of x and the sharing of y, and so I get the sum of x and y. Right? Same thing if I want to add a constant. I do not have to add it on every party. I have to agree on one party that adds the constant and done. Right? And if I multiply with the constant, everyone has to multiply with the constant. And then by associativity, I'm done. Here. The main thing is if I want to multiply two shares. This is where it gets complicated, and that's exactly the reason why I said multiplicative depth is an issue. The traditional way is you can build a system where all parties know a share of each input, and then after the protocol is run, all parties know a share of the output. If you are aiming for MPC in the head, you can actually do something nicer. You can do something where all parties know shares of the inputs and the outputs. Then you can run a protocol which actually proves that the shared output is the product of the shared inputs. Does this make sense? So you just prove that, we'll have this on the next slide. So if all parties have sharings of x, y, and z, after the protocol you have a proof that x times y equals z, without revealing these values. Why is this nicer? To do this, so in both cases I will actually need random secret sharings of multiplication triples, so values a times b equals c. Here I have to do a cut and choose approach, so I have to verify these, which means I have to generate like 10, then I'm opening 9 random ones, and if they are all really multiplication triples, I know that the 10th with the probability of 1 minus 1 over 10 actually is also correct. But this wastes a lot of multiplication triples. In this other case, I just need 1. So I will burn or will use 1 per multiplication, but that's it. So how does this work? It's actually pretty similar to the other approach. You need a random triple ABC, such as A times B, C. And so every party has a share of A, of B, and of C. And you want to verify that actually x times y is z for secret shared values x, y, and z. Okay? So what the parties locally do, first they get from somewhere externally a random element in FQ over which all operations are done. This is called sometimes the multiplication mask. And usually it's written as an epsilon, but PowerPoint Online doesn't have an epsilon, so you have to live with an E. But they have alpha and beta, so we actually are computing values of alpha and beta, where alpha is e times x plus a, and beta is y plus b. Then we're opening alpha and beta, so note that this actually doesn't leak anything about x and y, because without A and B, they are still one-time penalty. And then locally, the parties compute this equation down here, which is something that boils down also after this opening of alpha and beta just to local operations, so to constant multiplication, constant addition, and share addition. And then everyone broadcasts the resulting share of V. And if the secret sharing of V sums up to 0, then they accept, and otherwise they reject. Why should this work? You can actually compute this. I will leave you the slides, like you can look at this later. I'm convinced you this actually works. The interesting thing is if you look at soundness, like if someone wants to misbehave, what are the guarantees that I get? Then you see that we're actually using in the first step of the multiplication that z is x times y and c is a times b. And you actually need this. So let's assume that actually z can be written as x times y plus some difference dz. And for c we have the same with the difference dc. Then you can trace this through the computation and you will get that v is e times the difference in z minus the difference in c. Okay, which means that we can actually check what happens if one of these differences is not 0 or both are not 0. So which means that one of the multiplication triples is actually not a multiplication triple or both are not. And the claim is that if at least one of them is not 0, then the result of the computation is 0 at most with probability 1 over the size of the finite field over which we're operating. And the proof is pretty straightforward. If the set value is not a multiplication triple, if the C value is not a multiplication triple, then actually this thing becomes 0, so we will be exactly minus the difference, which is non-zero by assumption. If you look at the case where both are non-zero, if V is 0, then we know that dc is e times dz. It's just rewriting this thing. So this means that dc times d set to the -1 has to be e. This is a fixed value, so this event occurs with exactly probability 1 over the size of the field from which I'm picking. Right? Is some people nodding? This is important because the same reasoning will happen in the next line again. So we again come to the point that in this case, if just a different d set is not 0, then this part vanishes. So we have 0 equals e times d set. This only happens if e is 0, and that happens again with the probability 1 over the size of the space from which I'm drawing. And so this is 1 over f cubed. Okay, so if we're convinced that we can do this, we can actually look into what kind of, how do these circuits look. And an example that we will see in a moment is interesting is evaluating a shared polynomial in a public point R. Right, so we have a polynomial where the coefficients are secret shared, and we're evaluating it at a public point. Then we can actually compute these powers of the public value locally. I mean, this is just a constant which we can raise to some power. And then we have constant multiplication with the coefficients, and then we're summing local shares, also something that we can do locally. We get a single secret shared value. Doesn't need any interaction, single value as outcome. If we want to evaluate the product of two shared polynomials at a random point R, then we will actually need knowledge of the result set if we want to use this verification trick from before. And the idea is that we actually evaluate the two polynomials locally. Right? So we will then get some value y and some value x. And then we have to run the verify for this product of x times y input set. This step we can do locally, this step we can locally. This is this polynomial, this multiplication verification that we had before. Okay? I think this is the most complicated part of the whole lecture. So. And this is something that is used in the SD-NAT signature scheme. So here we're using some version of the syndrome decoding problem. Don't mind this too much. The only important thing is we have this equation here, which is the input x times some matrix gives me a given value y. If it was just this would be freaking amazing, because this is trivial to verify. This is a linear equation. You can do this all locally. Amazing. The problem is, this is actually not hard in general, but this is only hard if there's a certain bound on the weight of the x. So if you don't have this bound, it's easy. Why this is the case, Alex will tell you. But let's just say we have to make sure that our solution x is actually low weight. So linear function, great. Weight check, it's a bit annoying. So you somehow have to find a way how to do this, and this was the main thing of this SD-NAT paper, actually showing how to do this. And for this, we have a two-step process. First, to verify the linear equation, what you actually do is you can write this matrix H in a standard form where you have some matrix H prime and then some identity matrix. And then you can split X such that Y is this matrix H prime times X plus XB. And if I then define the secret key to just be this XA part, and during my MPC computation, I'm actually computing the full X by computing XB as Y minus this H prime times XA, then I'm implicitly verifying immediately that the X that I just computed fulfills this equality Y equals H times X, right? So by making sure that this is part of my MPC computation, I have the linear constraint check already in. Okay, so this leaves the weight check. How can I do this? I will not explain this in all detail because I'm still struggling a bit with the very precise details of how this works. But what you do is you build a polynomial s from x after you computed it from xa, h, and y. And you do this by interpolation. This is something you can again do locally. Then you generate polynomials depending on the weight function, q and p, and you have some public polynomial f. And the important thing is that they are generated in a way such that s times q minus p times f is 0 if the weight of x was within bounds. And in addition, I actually didn't put this on the screen, but we can control the degree of the resulting polynomial, and that degree is actually pretty low. And so what we do is later on, we check that this polynomial is equal to this polynomial, or that this minus that is actually 0 by evaluating it at random points from a bigger space. And if you have a degree d polynomial, this can have at most d roots, or at most d positions where it becomes 0 if it's not a constant 0 polynomial. So if I pick my points from a large enough space, the probability that I exactly hit these roots is vanishingly small. Or it gets smaller and smaller the bigger I actually take the space, and the smaller the degree of my polynomial is. So I can balance the number of points at which I'm evaluating these polynomials so that I get a reasonable success probability of getting anyone that tries to cheat. And so this is actually the equation that I will evaluate for a bunch of public points R. You might remember we've seen this equation just before. So this is exactly this multiplication of two polynomials evaluated at a public point. And so the MPC circuit looks like this. I have a secret shared xa. I have public values h and y. I compute the secret sharing of x from this. Then I generate this polynomial s in the secret shared form from the secret shared x. I generate these polynomials q and p in the secret shared form. The public polynomial f doesn't need to be secret shared because that's just known. And then I can actually use this protocol which we had before to evaluate this product of polynomials and check that this gives me another polynomial. Okay, and this is the function that actually the SDVAD protocol does. So it builds a zero polynomial and checks that it's really the zero polynomial by evaluating it at a bunch of points. Any questions about that? Everyone's done? Okay.
Well, then I ask something.
Yeah.
So where do you use the multiplication triple from this?
To verify this equation. So to verify that S evaluated at R times Q evaluated at R is P times F evaluated at R. So I know I have a secret sharing of the right hand side, I have a secret sharing of the two polynomials on the left hand side. And then I run the protocol to actually evaluate that this is really a multiplication triple. Yeah?
So for this protocol, it's enough to verify one of the shares? Instead of like 9 out of 10, you need to verify just one MPC view?
No. So this actually is done with all the parties that have these independent shares of these values. And if they all do this, then they are together in the end convinced that this is actually the case.
Okay, but then, yeah, maybe you're not...
So this is just MPC computation. This is like we have n parties that together do this computation, and afterwards they are convinced that they are holding a secret sharing of the product of these two values. But you're right, the interesting part then happens afterwards. We want to turn this into an identification scheme. And this is where the actual MPC in the hype part starts. let me first give you a bit more detail of what these identification schemes are before we take a break. And so, these go back to the concept of zero-knowledge proof, so it depends a bit on if you're reading in the crypto literature or more in the complexity theory review literature. So they were invented by Goldwasser, Samikali, and Rakov in '85, and they're a form of interactive proof system, where one side tries to convince the other side of a statement by running an interactive protocol. And the interesting part here is you try to prove knowledge of a secret without actually revealing any information about the secret, which in the first moment might sound a bit absurd, but this actually works. And if you're a bit more into crypto and you like classifications, it's actually not zero-knowledge proofs that we're interested in, but we're interested in honest verifiers, zero-knowledge arguments of knowledge. Who cares? Let's say identification schemes, and we will talk about the properties that we need in a moment. And they look the following way. We had this picture now a few times. The prover starts with a function called the commitment that gets the secret key, possibly some randomness, produces a commitment W. Why is this called W? Don't ask me. This goes to the verifier, who has the public key, and we are interested in verifiers which are public coin. Public coin just means that they are just sampling the challenge from some set in a random way. So they don't do any complicated computation, they just pick random coins, send them back as a challenge. Then the prover reacts to this challenge by computing a response based on the previous commitment, the secret key and the challenge. This goes over to the verifier can run a verification algorithm on the full transcript, so the messages WC set together with the public key, and then outputs a decision B, which is usually 1 if you accept and 0 if you reject. And these 3-round versions of these protocols are called Sigma protocol, because they look like a Sigma. Right, so let's look at an example that actually demonstrates all of this in quite some detail. I guess everyone in the room knows Sudoku. Now you can make a Sudoku, and if you give this to someone, this person might want to be convinced that this is actually solvable instead of wasting their time in playing this. I mean, some of these books actually, I think, just are generating these things at random, such that they have a high probability of being solvable, but they are not always. Anyway, so how can you prove that a Sudoku is solvable without actually leaking the solution? And this is something that you can do with these zero-knowledge proofs, and this works as follows. Let's say Alice wants to prove this, so Alice develops a Sudoku, which is solvable, and this one is actually consistent. I think I checked. I tried. The first thing she does is she applies a random permutation to the solution, which gives her a new Sudoku, just by relabeling. This is actually, if you want to generate Sudokus, it's an easy way to get cheap Sudokus. So this gives you a new Sudoku. The next thing she does is she prepares a scratch card, and the scratch card is actually a nice pen and paper example of what a commitment scheme is. So a commitment scheme is something that hides its input, but allows you to later open the input that you put in a way that you cannot change your mind. Like, you cannot later on go and say, like, no, actually I meant this. So you really are committing to the input, but such that it doesn't leak. And later on you can actually reveal it if you want. Okay? This is something that they use, for example, in auctionings. Like, then you commit to your bid, everyone gives in their committed bid, and then you can open all at once. And no one can adaptively change their bid to go higher than the others at a later point. Okay, so we have this commitment. And actually you're not committing to the full thing at once, but you're committing to every cell independently. And then Alice gives this to Bob and allows him to do one of the following things. So Bob can either scratch off a row, or he can scratch off a column, a square, or the original Sudoku. The idea is, if I scratch off a row, I can verify that every number appears exactly once. The same for a column and the same for a square. Right? If this is a valid Sudoku, this has to happen. And the last one shows that I really applied a permutation and didn't do some other, like didn't put just some other Sudoku. And then, so Bob can always check one of these. Any idea what would happen if you can check two of these at the same time?
You can reveal more information?
Yes. You will actually learn a bit of the Sudoku. Right? Because, for example, if I get the permutation in one of the squares, I know exactly which numbers actually go. Okay. So, what does Bob gain from this? If he catches an inconsistency, obviously he knows Alice cheated. The problem is, if he does not catch an inconsistency, this doesn't mean that Alice didn't cheat. This just means that he didn't catch it. So, there's still a chance that Alice might have cheated. However, Bob actually gained some confidence that Alice did not cheat, because he would have caught her with a certain probability. And so, if you look at the details and crunch the numbers, you see that this actually gives you a 27 in 28 probability of Alice to cheat. But you actually catch her with a probability 1/28. And what you can do now is you repeat the protocol over and over until you're convinced enough that Alice didn't cheat. Right? So if you want to get to a 0.99 probability, you have to run this about 2,500 times. So this protocol actually sucks. But in the end it works, and this is the principle that we actually also use for cryptographic protocols. We just don't have such a bad soundness error here. Because, so this is what we call a soundness error, is this term. Yeah. Any question about that?
So if Bob can repeat that test, then he gradually learns about the entire Sudoku.
This is very important. There is an important thing in here. If you're repeating this, you have to start the protocol entirely from scratch, which means you have to redo the permutation. Like you have to do pick a new permutation, then you actually do this, and then you will actually not learn anything. And that you cannot learn anything, this is what we prove by honest verifier zero knowledge. So honest verifier zero knowledge proves that an honest verifier that doesn't misbehave doesn't learn anything. And so here we want to show that Bob actually, if he doesn't misbehave, cannot learn anything about the secret that he couldn't have generated himself. Right? I mean, obviously we know that if the secret is correct, then we have all these rules, like in one square, you have every number just once, and so on. So this is nothing that they wouldn't know. And we can prove this by actually showing that Bob can generate transcripts. And actually transcripts, which are indistinguishable of transcripts that would be the outcome of an honest run, of an honest interaction between Alice and Bob. How does this work? The main trick is all the soundness guarantees come from the verifier knowing the sequence of actions. Right? The commitment makes sure that you cannot pick your values after you know the challenge. But if I can actually generate a full transcript without interaction, I can first pick the challenge and then I can do the rest as I like. So what I will do is, I first pick a challenge at random, and then I produce the scratch card. And I just don't care about the things that will not get scratched off, because this is anyway hidden. The only thing I have to care about is the square, column, or row, or if I have to open the original Sudoku, the permutation. So I pick this one uniformly at random and place it there. And this will be indistinguishable from what Alice gets. And this is exactly the same distribution. I will just put a random permutation of 1 to 9 into the row if I have to open it. And this is exactly what Alice has there. She actually knows the secret. And the same for the other parts. And this means I really, like Bob, cannot have learned anything from this interaction. And this is actually pretty nice because it has been shown that the solvability of n times n Sudoku is NP complete, which means, in general, this proof already bootstraps to a generic proof for any other problem in NP. So just by knowing how to prove Sudoku, you can actually prove knowledge of a solution to any NP statement. You just have to transform your instance into a Sudoku instance, which of course is the tricky case.
How do you do the squares for general n?
Then your n just gets bigger. I mean, you need square n's which are squares. Otherwise...
No, but it's 9 by 9, no?
No, but you need your n, so the 9 has to be a square. Otherwise it doesn't work. I mean, otherwise you don't get a meaning. Well, you probably could do a Sudoku instance, which still... I don't know. Let's agree n is square.
You could have rectangles, but you don't have square and
But then they have to go.
I think at this point we can take a short break, and then I will tell you how you actually build such an identification scheme from an MPC protocol.
Okay.
So be back in 5. If someone wants, or to answer questions. I have to admit, actually preparing this talk, I first understood certain things about these protocols myself, also I already was working quite a bit on these. So there are some intricacies which are non-trivial, I would say. Right, so now we have some idea of what an identification scheme is. Yes. And while I described this just before with Alice and Bob, let's get a bit more serious about the security properties that we want. So we have 2 properties and a special version of the first one. The first property is soundness. And that says that a prover that does not know a secret will actually get caught with high probability. And the probability is 1 minus e, where we call e the soundness error. Again, this will be an epsilon in 90% of the papers that you see. PowerPoint and Linux. We have seen E was pretty bad for the Sudoku case, which translates to massive inefficiency. But if you have reasonable sized E, so significantly smaller than 1/2, then you actually are on a good way. Then we have special soundness, which is something that you can get from soundness for certain schemes, and we will see that the schemes that we are interested in actually has this. And this says that if there exists an algorithm that we call the extractor, which when you give it 2 transcripts of the scheme, such that the challenges in the transcripts differ, but the commitment is the same, you can actually learn the secret. If you have something like this, then you actually get nice proofs afterwards for the signature schemes. So this is something that we're aiming for whenever possible, because it's a lot nicer to work with than general soundness. And then we have this other property called honest verifier zero knowledge. And this speaks about the second efficient algorithm, which is called the simulator, which was called Bob before. So the simulator should be able, given only the public key, not the secret key, to produce transcripts which are indistinguishable from the one that actual protocol executions generate. Right? So if this is possible, then this actually says that an honest verifier will not learn anything about the secret. Good. you can actually have multiple round schemes. So in a post-quantum setting, you will see a lot, at least 5 round schemes. I think all the protocols in the current signature on-ramp are at least 5 rounds, if not more. And so this can actually go to 2n plus 1 rounds for arbitrary n greater than 1. I think the biggest one is 7 right now, but I think Feast had 9, if I'm not mistaken. So this can get quite high. We usually require that this initial commitment message has high entropy, which means it's hard to predict. This is something that allows you to avoid to have to put additional randomness in there if you later transform this into a signature scheme. We get a nicer signature scheme later if we have property in the IDS, which is called commitment recoverable. This is pretty nice because this is the case if you have a function that, given the challenge and the final response, allows you to recompute the commitment message and thereby to obtain a full transcript, which means later our signature will essentially be a transcript of the identification scheme. And so if I can compute W from C and Z, I don't have to include W in the signature. Right? So this means I can save actually quite a lot. And we will later need a negligible soundness error, read extremely small, not 0.99, but more like 2 to the minus 128. And as I mentioned, this is something you can get via parallel composition. So I'm just running this protocol several times in parallel. I have to do all these randomization steps independently for each of the iterations. And if I do this often enough, the cheating probability will actually get small enough that I get security in a cryptographic sense. Right? I mean, if you want to convince a friend, I think 0.99 is actually fine, but if this is about your credit card data on the internet, I wouldn't do so. So, how do we get such an identification scheme from MPC in the head? This is something that goes back to a stock paper from 2007 by Isai, Kushilevitz, Ostrovsky, and Sahai. And we just had this discussion. I think this was actually in the context of masking, so something like how do you make secure hardware implementations, but really took off in the context of post-quantum signatures. As I mentioned, the idea is, given a one-way function, I create an identification scheme which proves knowledge of an input x, such that evaluating f at x gives me y, in an honest verifier zero-knowledge way. And so my secret key will be x, my public key will be y, and potentially a description of f. Okay? And on a high level, so simplifying a bit here, the protocol looks as follows. I'm running my MPC computation as prover. I'm simulating this, which means I'm splitting my x into a secret sharing. I'm evaluating the circuit that I generated that computes f if called on the secret sharing of the input x. And then I commit to the inputs of every party independently. So I get one commitment per party. And in addition, I include all the communication of the parties, and I set this over to the verifier. The verifier picks a challenge, and this challenge is just a random party. And then, receiving this challenge, the prover will open all parties except the one indicated by the challenge. Okay, so this means I'm opening all the randomness that these parties use, I'm opening all the input shares, and that's it. And this actually is the stuff that I also committed to before. So this then gets sent over to the verifier, and the verifier opens these parties, checks that they get the same communications when running these parties together with the communications of the unopened party, which they got from this step. Right? This was already in the commitment message. And they also check that actually the final result is the intended result. And usually we build these schemes such that the result of the whole circuit should be 0. as in a multiplication check. Right, so why does this give me soundness? We said the MPC protocol is perfectly correct if no one misbehaves. Right, so if I want to convince someone that the result is indeed 0, if I don't know an input which evaluates to 0, then I need to misbehave in the name of one party. I shouldn't misbehave in the name of two, because then I will get caught anyways, right? Because all but one party get opened. So I will misbehave in the name of one party, which means I will actually produce communications, marked in red here, which I think you cannot see, maybe on the screen's better, which do not match what the input would actually produce. When do I get caught?
When you use final log?
Mm-hmm.
When you use final log?
No, in this case, I don't get caught when I compute the final output, because I'm choosing these communications exactly such that the final output will actually be correct. I will get caught, well, I will not get caught, actually, exactly in the single case that this party does not get opened. Right? Because in this case, the verifier only sees the communications of this party, but cannot check if they actually correspond to the internal state of the party. So everything looks fine. But if the challenge is any other value, which means that I actually have to open this one party, then it's over for the attacker. So in this case, I will get caught. Because in this case, you can just run this party, avoid the communications, and you will see that the communications produced by this party actually don't match its inputs. Right? And so this means there's exactly one challenge value with which I will not get caught, and so if I have n parties, I get a soundness error of 1 over n, which is pretty nice. So this is pretty easy to scale. I also get special soundness, and I think in this case it is pretty obvious. If I get two openings for different challenges, which verify correctly, then I learn all the secret shares of x. Which means I can just recombine, right? I just sum up all the x, I'm happy. Honest verifier cellular knowledge works exactly the same as for Sudoku. The trick is that I actually sample the challenge first. When I sample the challenge first, I can just pick all the parties that will get opened, somewhat like with random inputs, but honestly, so that actually their computations make sense. And then I just pick the communications of the unopened parties such that they give the result that I want. And you will see, like, you can actually check this if this will actually give you the correct distribution in this case. So this was a bit simplified in several dimensions. One dimension I actually want to clarify this, and this is, if you remember, we want to do an MPC computation where we do this multiplication check, where we need this E, which is an epsilon in real life, as a randomness that comes from outside. This means this is actually something that has to come from somewhere, so we have to add a round trip. And actually for ST and the heavy, in addition, these points are in which we want to evaluate the polynomials. So, that means, in the beginning, I share my secret x, I generate the required number of multiplication triples, and I commit to all of these per party. Right? So I take all the shares from one party, put them together, commit to them, this gives me one commitment per party. Then I send all these commitments over to the verifier. In response, the verifier sends me these t random values e, these multiplication masks, and in case of SD in the head, t additional random points on which I am asked to evaluate the polynomial on. And then I'm actually running the MPC protocol with these additional inputs. I assemble all the communication and send all these communication of the multiplication verifications back to the verifier, which then sends me the original challenge, which asks me to open all parties but one. And then I open all parties but one, and the verification checks, as before, that all the open parties actually, when you run simulating them again, give you the communications which were given in the second message, and that the final result is correct. Right? And it's really important that you actually first commit to the inputs of the parties before you get the randomness, because otherwise you can cheat this multiplication trick. This was also something that the Biscuit people actually got wrong. At least in 3 out of 4 drawings of the protocol. Yes. So what's the impact on security? Honest verifier, zero knowledge. This really doesn't make any difference. I'm just sampling both challenges in the beginning and simulate everything. Works like a charm. For soundness, things get a bit more nasty. So now I suddenly have 2 ways of cheating. Right? I can cheat this multiplication test, and I can actually just produce wrong interaction transcripts. And so my soundness actually becomes the sum of these 2 cases, as bounded by this, my soundness error is bounded by 1 over the size of the finite field plus 1 over n. What's a bit more nasty is that I actually, my special soundness definition becomes a bit vague. So we're currently working on a paper where we give a closed definition of this. In short, you cannot really give a special soundness definition anymore, because if I'm allowed to choose the full transcript, I can actually cheat this multiplication test. So that's why this is a bit problematic. But you get some form of special soundness. You get computationally bounded adversaries or computationally bounded circuits which produce the transcript. So that may be in short. And this is really just a definitional issue. There's a bunch of optimizations for this whole thing. I mentioned this before, so you can actually generate all the shares uniformly at random, which means, because these shares are usually much bigger than n bits, which is like the minimum size you would need for security, you can generate them sampling random seeds and then using a pseudo-random generator to expand them to the necessary size. In this case, you can of course not control them and make sure that they sum up to x, so this means you have to compute the delta between x and the sum of these. And this delta, you just have to make sure that this is known to the verifier. So you can include this in the first message and everything is fine. But you have to include it. So this was actually the thing the Biscuit people didn't do. And then you're not committing, if you're then just committing to the shares, you're not committing to x yet. The second thing you can do is you can use what's called a tree PRG. You might notice GGM PRG, which takes a length doubling PRG and always produce 2 new seeds, and then from this you can produce 2 new seeds and so on. This has one beautiful property. If I generate all the inputs of one party from a single seed, then I can actually, I have to open n minus 1 of these seeds, right? And I can open something like an authentication path, which you will hear about tomorrow, in this tree, which has 1 node per height in the tree, which will open all of these n minus 1 seeds. So this gives me kind of a log size opening in place of an order of n opening size to open n minus 1 parties. And finally, I can actually hash the commitment message. So I take all these commitments and the communications which I would send there. I hash them all together, which gives me some form of a hash-based commitment. And then only in the final answer, Well, I include the opening information, which I would have included before. In addition, I'm including the unopened commitment. And I have to include all additional information that was in the first message, like in our case, the communications. Right? And then later, I can actually recompute the initial message, hash it, and check as a verifier if this really matches this W value. There is another optimization which we proposed at Eurocrypt last year. And this is something that you can think of as batch verification. So the idea is, if you remember, the soundness scales with the size of n, right? So if I increase the number of parties, I get better soundness. But if I increase the size of the number of parties, I actually have to do more MPC computations, because every party has to run this protocol locally. And so what I can do is, because everything is additively homomorphic actually in this protocol, I can, for example, if I want n parties, I can still use n parties, but I can run 2 3-party protocols instead of 1 9-party protocol, which means I have to simulate 6 parties instead of 9. By grouping my what we call the leaf parties along a dimension. So for example, in this case, for this one, we're grouping the parties in terms of the columns. We just sum them up, and they give us what we call then the main parties, among which we're running the protocol. You do the same for the rows, and you can do this in arbitrary dimension. Like you're just projecting along one dimension, and by that you get these different main parties. With these, you're running the protocol, and your challenge will still be one of the leaf parties, which prevents you from opening exactly one of the main parties in every dimension. Right, so the commitment still works the same as before, the opening works the same as before. The only thing is that the MPC computation you're not doing for every leaf party, but you're doing for these combined parties. And thereby you have to run this with less parties than you actually would. One could have the smart idea to say like, hey, why do I actually have to do this? I can just run 2 independent 3-party protocols. The problem is, if I do this, I will actually have 2 of these aux values. These aux values are these deltas that I compute if I'm generating all the shares at random via PRGs. I still need these offsets that they actually sum up to the right value, right? And these offsets are far bigger than the actual values, so having to include 2 of them blows up my signature size significantly. And this allows you to do several of these protocols. If you look at it from a different point of view, you can do several protocol runs at the same time with just a single aux value. Good. I'm good in time, so I will briefly talk about the final step, which is VHIME. So now we have this interactive protocol, which is great if you want to open doors. So this stuff is really, identification schemes are what's used in car opener, like car keys. Now this whole home automation, door locks and so on, at least if they're somewhat secure. But what we actually want is some non-interactive protocol, right? We want a protocol where a signer actually has a secret key in the document, produces a signature, this thing can be stored away, they have to never meet the verifier gets this document and a public key and can verify that this was actually signed by the signer. Even if the signer is long dead and I don't know, like this stuff is, you can archive digital signatures and so on. So this has a bunch of reasons why you don't want interaction. So how do you get there? On a high level, this is pretty plain stupid. You just compute the challenge as the hash of the public key, the commitment, and the message. Right? So the challenge before was a random value. I'm taking the verifier out of the loop. So the verifier now only has the verification algorithm left. And the signer, instead of asking the verifier to send a challenge by sending first the commitment message, simply computes it as the hash. And the verifier does not only have to run verify, it also has to run a verification of this hash, of course. But that's it. And then I have a signature. A signature is just the transcript of the protocol, as I said before, and you verify this transcript as a verifier. So, why is this secure? If my identification scheme was... I thought you might have seen when signature schemes are secure. I noticed you did not. Okay. So, what does it mean for a signature scheme to be secure? We assume that even if an attacker sees you signing several messages, and even if they can choose the messages that you're signing, they cannot come up with a signature on a message that you did not sign. Right? So they get your public key, they get access to an oracle which signs arbitrary messages they sent there. And after seeing Q of these signatures, they should still be unable to produce a valid signature under your public key. This is what's called existential forgeability under chosen message attacks. So, the proof for these protocols actually works in two steps. I'm first taking care of this oracle and show that if I have an attacker against, like for chosen message attack security, I can turn this into a no message attack security attacker. So that doesn't need any oracle. And this is using the honest verifier zero knowledge property of the identification scheme. What I will do is I will simulate a signing oracle by using the honest verifier zero knowledge simulator. If you remember, the simulator spits out transcripts. My signatures are also transcripts. The only thing I have to make sure is that actually, so that they are transcripts, but they have this little property that the challenge in the transcript is actually the hash of the commitment message and the message that gets signed, and potentially the public key. So what I'm doing is, I'm using the random oracle, my good old friend, and I'm programming it, given the transcript, such that this transcript and the message actually is consistent with the challenge in the protocol. This is classically, you can do this pretty easily. If you ever did a random oracle proof, this is kind of the easiest one that you can think about. Even quantumly, this is somewhat doable. We have black box theorems which tell you that you can actually reprogram a random oracle as long as the output value is uniformly random and the input value has sufficient entropy. If you remember, I said some time ago, we need that W has enough entropy. This is why. Right? So if W has enough entropy, the probability, so the intuition is the probability that the attacker has queried H at a position that contains W is actually small. It's like related to the entropy of W. And so if the adversary never queried the hash function at position W, M, I can change the function there without the adversary actually noticing. And then I get valid signatures because these transcripts are valid. And they are suddenly consistent because I'm programming the random oracle. The second part is soundness, and this is, I think, one of the most complicated proofs in basic crypto. This was also, I think, one which was the hardest to solve in the QROM so far, and we only have really nice results for special cases. Intuitively, the idea is that you cannot do better than guessing the challenge per hash query, right? So I'm picking as input my commitment, and then I get a challenge. And in my commitment, I actually have to guess the challenge to be able to misbehave if I don't solve the underlying hard problem and so on. And so for every query, I actually make one guess of the challenge. If I hit, I succeed, and if I miss, I fail. And soundness tells me exactly what the likelihood is that I succeed here. Proving this is a nasty business. We have a tight proof for the special case of 3-round committed open identification schemes for special soundness. And luckily, if you remember, this is what we have in the MPC in the head case, as long as we're not in this real world setting. Right? So the real world setting was 5 rounds, that's even 3 rounds, good, 5 rounds, meh. We have, in theory, proofs for the other cases, but they have massive loss. So if you are nitpicky, then you could say for practical parameters, they don't say anything, because the tightness loss is so massive that you cannot relate this to any reasonable hardness of a practical problem without blowing up things that they are totally impractical. In the committed open ID protocol setting, the idea is that if you have an adversary which can forge with a success probability greater than the soundness error, then they must be able to open for more than one challenge. And so if you use a random oracle in place of a commitment function, you can actually look at what the adversary committed to, even if they don't open. And you can reason that they must be, like, if they are able to open for more than one challenge, this means that all the committed values must actually be correct. And you can extract from why the random oracle can sum up, and you actually get the secret key. Yes, that's the intuition there. As I said, this works for 3-round committed open. I don't have any time to go into this in detail because I would have to explain too much. But what we showed at AsiaCrypt last year is that you can actually turn this SD in the head identification scheme into a 3-round identification scheme if you're also replacing this first challenge by the hash of the first message. This is some form, again, of this Fiat-Shamir transform, but you can actually get a nicer proof because you don't need honest verifier zero knowledge for this proof, for this step. So this is just a search problem which you can find a reasonable bound for. Then you get some form of special soundness, which we call query-bounded special soundness, where you have to assume that your adversary doesn't have the complexity that they can search for a first message, such they can actually cheat the multiplication test. Right? And then you can apply this result for 3-round committed open identification schemes in the QROM, which I didn't have time to figure out the reference, but this was Chris and Christian Mayens, who's also one of the supervisors in the team, I think Jeladon and Serge. Yeah. Something soundness of committed open Sigma protocols. Yeah. And so you can actually make this work, and we're currently working on, I have a work that shows that you can do this in more general. So this approach actually works for most of these schemes. You can first make these probabilistic tests for some additional properties, non-interactive. And then you can apply this Fiat-Shamir for the 3-round scheme, and then you actually. And that's it. We have a signature scheme. Was easy, wasn't it? So, what did we do? We started with the one-way function. We secret sharded its input In addition, we turned the function into a circuit which, when evaluated on a secret sharing, gives me the output of the function on the secret shared input. From that, we got a multi-party computation protocol by running this circuit as a multi-party computation. Then we did MPC in the head to build an identification scheme, right, where we're simulating each of the parties and we're opening one party based on the challenge to check that they all behave. And then we make this non-interactive file for each other. And so this is really nice because it allows you in theory to build a signature scheme from any one-way function. The question is just how efficient it gets. It works best for functions which are mostly linear, because as we've seen, linear steps are cheap. You can do these locally, you don't need any additional secret sharings, or great. There's a bunch of nice optimizations, and I'm pretty sure there are more. Like there's recent work which says you can also do this with threshold secret sharing, and then you can actually get a bit better soundness, and that translates again in smaller signatures. You don't need a structured problem. We had a proposal that you can actually artificially increase the cost of the hash function calls. Thereby an attacker can just try less inputs, which means you can keep your challenge space smaller, which means you have to run less parallel repetitions of the protocol, thereby your signature size goes down. So there's a bunch of things that you can actually still do. And looking at this, we get actually quite competitive schemes. So secret keys and public keys are really small. The signatures are in a medium range. You don't get as small as Dilithium or Falcon, but you can actually by now meet Sphinx at the same security level. This stuff is actually relatively fast. So we're talking about a few milliseconds. A bit of a drawback is that they take as much time for verification as for signing, which in certain settings can be an annoyance. And you have this nice property that you have online-offline signatures. So actually, if you do the switch to 3 rounds, you only need the message in the last challenge hash, which means you can compute everything before this last challenge in the final opening, before you actually see the message. So you can do pre-computations. And then the online phase, you can see here, is just in the 10th of milliseconds. So that actually is pretty quick. That's it from my side. Any questions?